Yeah. Zero squared is one. Yeah, that's what it is. So,
Oh, yes. Raise to zero.
Yeah, you're right. Yeah, 0 minus 1, which is negative 1. So it'll be negative 1. I know what
so calculator.
negative 1 divided by negative 1. Yeah.
And then
How so? Oh, that's an interesting
I
idea.
think this one is 0. Yeah.
Oh, is it the same? Oh, how does g of x behave at points other than 1?
The second one is the exact same, except it's got like an asymptote.
Exactly the same as x. Good food for thought. As always, feel free to flag me down if you have any questions. Well, it depends on how it's undefined. Like if it's defined everywhere near but not at a single point, then you would just draw like an open circle. If it's something like f of x equals square root of x at x equals -5, where it's not defined anywhere near there, you just wouldn't include that association.
Okay.
In this case, I'm guessing you're saying this is only undefined at 1 for g of x, then you would just draw like an open circle. What's that?
Asymptote.
Ooh, what's that doing?
You just need
It just shows that it can't equal 1 at that point.
I would actually disagree that there's an asymptote there.
Right.
Usually you would have like a vertical asymptote like that as x gets close to 1, f of x went up, shot up to infinity or negative infinity. Doesn't look like it from looking at it from your graph. So, yeah, we're going to talk about asymptotes later on, but for now, I would not include one there.
Yeah.
Although you're right that asymptotes do usually occur at points where it's undefined. I just don't think this happens to be one of those scenarios.
For geometry, so that point is like undefined. So it's, I thought they were like both the same line, but at x equals 1, there's a circle. Where's that?
Having some troubles? Oh, you have troubles with your names. Do I need to chastise them? Be better. We'll come back together in another minute or so.
Yeah.
Alrighty, let's come back together, and I want to talk about this function. Can anybody read me off their table or their f of x row from the table that they filled in? If we're plugging in the values 3, 2, 1, 0, and -1 into the function f of x equals x plus 1, what did you all get as outputs?
4, 3, 2, 1, 0.
Like so? Everybody on board with that? F of x, pretty straightforward. It's a linear function. No matter what you plug in for x, your output's just going to be 1 greater. And if we were to graph f of x, it would look something like -1, 0, 0, 1, 1, comma 2, 2, comma 3, etc., etc. Straight line with a slope of 1 and a y-intercept also at y equals 1. So now I want to look at g of x, which is a little bit spicier of a function. Let's see. We plug in g of 3. We're going to get 9 minus 1 over 3 minus 1, which I'm getting 8 over 2 is 4 for my output. Okay, that's neat. When I plugged in g of 2, I got 2 squared is 4 minus 1 over 2 minus 1, which I got to be 3 over 1, which is 3. Okay, that's interesting. When I plugged in 0, I got 0 minus 1 over 0 minus 1, using the fact that 0 squared is just 0 times 0 is 0. Gave me a -1 over -1 and gave me an output of 1. Oh, hey, that's interesting. When I plugged in -1, I get, let's see, -1 squared is positive 1 minus 1 over -1 minus 1, which I got to be 0 over -2, which simplifies to 0. Huh, that's odd. What happens when we plug in x equals 1 into our function g of x?
We get 0 over 0.
We get 0 over 0. We get sadness. Well, let's see. If we plug in x equals 1, we'll get 1 squared is 1. So we get 1 minus 1 over 1 minus 1. 0 over 0, which is equal to
Sadness.
does not exist. Undefined. You're dividing by 0, and you don't want to divide by 0. So we get something interesting that happens, which is g of x values and f of x values, to me, appear to be the same in most places. At every value, at first 2 values of x I asked you to look at, the last 2 values of x I asked you to look at. But at x equals 1, we've got some shady business going on. So if I were to graph g of x, what do you think that would look like? Specifically, how would the graph look like in comparison to what our graph of f of x ended up looking like?
It's
Yes, I see you. I'm just giving up.
it's the same line, but there's an open dot at x equals 1.
And x equals 1?
Wait, no. At 1, 1, 2, or yeah.
So
But essentially, otherwise it's the same points.
something like that. Something like that?
Yeah.
And then otherwise you said it's going to behave the same way?
Yep.
Huh. Interesting. So in other words, you're saying like our graph of g of x is basically going to be a straight line like f of x, except we have this big hole in it at x equals 1, owing to the fact that at x equals 1, g of x is undefined. Question, are there any other values of x for which g of x is going to be undefined? Meaning, are there any other values if we tried to plug in for x, we would run into trouble? Don't think so. Mainly because x squared minus 1, you can plug in anything for x into that, get an output that makes sense. You can plug in any value for x into x minus 1 and get an output that makes sense. There's nothing scary going on like square roots or anything here. I think the only problem that g of x could have is if you were to divide by 0, which is only going to happen when x minus 1 is 0, which only happens when x equals 1. So I think g of x is going to be defined everywhere except at x equals 1. And everywhere else looks to me like it's just going to be a straight line. So, any questions or comments about either of these graphs? Are these the same function?
I mean, it's weird because you can simplify x squared minus 1 into x plus 1, x minus 1, and then divide both sides by x minus 1. Maybe, I don't know if you're allowed to do that, but...
Oh, like, spoilers.
Yeah, and then you get x plus 1, so it's the same function.
So my next question was going to be, did anybody try and factor g of x in a way that made things simplify? And yeah, I think you're on the right track. So, let's not erase the original function. So, turns out g of x can be rewritten in a way. So, how did you choose to rewrite it?
X plus 1 times x minus 1.
Okay. Yeah, we can factor x squared minus 1 using our difference of squares formula into x plus 1 times x minus 1. And what did you do with that?
And then cancel out the x minus 1s.
Gave it the old swoosh swoosh. Say you have a factor of x minus 1 in your numerator. You have a factor of x minus 1 in your denominator, so that g of x just turned out to be x plus 1 in disguise. Imagine that. So I'll ask the same question I asked before then. Are these the same function?
They aren't, because when you factor that out, you lose a piece of information that x cannot equal 1.
Ah, interesting. We lose a piece of information when we do the old swoosh swoosh on our x minus 1 factors, which is, if you tried to plug in x equals 1 into g of x, we got sadness. We ended up with 0 divided by 0 cannot be evaluated, does not exist, undefined. But if we tried to plug in x equals 1 into f of x, well, it's literally 1 plus 1 equals 2. So, I would actually agree. I do not think f of x and g of x are the same function, despite the fact that with g of x, if we were to try and factor out the numerator and cancel out factors of x minus 1 in the numerator and denominator, they end up coming out to just x plus 1. So let's write this down. So the question of, are f of x and g of x the same function? I would say no, because f of 1 exists, but g of 1 does not. What would be another way of saying that? We could say that x equals 1 is in the blank of f of x, but it is not in the blank of g of x. Yeah, another way to say that would be to say x equals 1 is in the domain of f of x, but not the domain of g of x. Where I'm guessing domain is a word a lot of you have likely seen before. In general, we say that the domain of a function is just the set of all values you can plug into the function and get an output that makes sense. I'll write that kind of maybe as over as an aside. The domain of a function f of x is the set of all valid inputs into the function. We could say that x equals 1 is a valid input into f of x, because you could just take 1 plus 1 to get 2. But if you tried to input 1 into g of x, sad times happen. Yes?
Would you also be able to say that there's a discontinuity at x equals 1 in the function g of x?
Ooh, what does that mean?
Like there's a hole in the graph.
Ah, stay tuned for standard 3, where we will be talking all about discontinuities. But yes, we could. That would be kind of another, I think, equivalent way of saying that there's a discontinuity at x equals 1 where the function jumps and behaves differently. Or that the limit as x approaches 1 of g of x does not equal g of 1, using language we'll talk about in the next standard. But yeah, that would be another kind of valid way to say how are f of x and g of x behave differently from each other. What about at x? What about at values of x that are not equal to 1? Do f of x and g of x behave the same way everywhere else?
Yes.
Yeah. Looks like it. I would say if we were to plug in any value of x, no matter how crazy, into, let's say, x equals 5 trillion, you would end up, if we plugged it into the factored form for g of x, we would get 5 trillion plus 1 times 5 trillion minus 1 over 5 trillion minus 1. These two terms would cancel out, and we would just be left with the 5 trillion plus 1, the same thing that we would get if we plugged 5 trillion in for f of x. So we could say f of 1 exists, g of 1 does not, meaning x equals 1 is in the domain of f of x but not of g of x. And then I'm going to add as sort of an aside here, even though f of x is equal to g of x for all values x not equal to 1. Meaning if you were to plug in any value for x into either of these two functions, you're always going to get the same thing, as long as that value of x is not 1. Questions, comments, or concerns about the front page? Upshot is, you can cancel out 5 trillion minus 1, whatever that is, I'm not going to say it, from the top and bottom. You can cancel out a factor of 2 from the top and bottom, if we were to plug in x equals 3, say. If we were to plug in x equals 0, you could cancel out a factor of -1 from the top and bottom. Can't cancel out a factor of 0 from the top and bottom, which is what we would get if we tried to plug in x equals 1. So, what is this now? Dr. Gerstle, on the front page of the packet, you used a big scary word starting with the letter L, namely the word limit. Maybe that's not a scary word to you. I'll see if I can make it scary by the end of this one. If you notice, what would happen if we tried to plug in x equals 1.9 into g of x?
really, really close to 2.
Yeah, we get, if we plugged in 1.9 as an output, we get, oh wait, if we plugged in 0.9 as an output, we'd get 1.9 as an output. How about if we plugged in x equals 0.99999? We get y equals 1.99999 as an output. Or if we went to the other side of 1, plugged in x equals 1.0001, we get y equals 2.0001. So if you notice, for x close to 1, f of x is going to get close to an output of 2. And the way we're going to denote that sort of mathematically, oops, sorry, that's supposed to say g of x. And it's true for f of x as well, but it's more interestingly true for g of x. And so something we're going to say is that the limit as x approaches 1 of our function g of x is going to be 2, to denote the fact that for values of x that get really, really close to 1, if we're taking a limit as x gets super close to 1 but not actually equal to 1, we're going to get y values that get really, really close to 2. And that is going to give us our definition of a limit. So in general, we can say, given some function f of x, that the limit of f of x as x approaches some value we'll call a, is going to be a number L if as x gets really close to a, closer and closer to a, f of x gets closer and closer to L. And our shorthand for this is just going to be to say limit as x goes to a, usually you just write out lim for limit, and then a little x arrow approaching an a to say x is getting really close to a of your function f of x is equal to L as a shorthand. Essentially saying that if you have some value a, that's going to be an x value, even if the function behaves differently at the point A, let's say we have a filled in point way up here at y equals 2 instead of at y equals 1, and this is just some, I don't have a formula for this, just some function I drew up on the fly, what would we say f of the point A is going to be equal to? Meaning, if we were to plug in a exactly into our function, according to our graph, what does it look like we would get as an output?
2.
Yeah, at the point A, you would get an output of 2. But if we were to ask the question of what's the limit as x approaches a of our function, meaning if we look at values that are just a little bit to the left of a and a little bit to the right of a, what does it look like our outputs, our y values, are going to be really, really close to? You get outputs that are close to 1 rather than to 2. So in this case, we have an f of a and a limit that are not necessarily going to be the same value. because we have, yes, I'll call it a discontinuity, and we'll define that more carefully in standard 3. But A here is going to be a point where even though the function gets really close to 1 near A, at A itself, it takes on a different output entirely, an output of 2. So let's go back to our 2 functions here. We said for g of x that g of 1 is undefined. G of 1 does not exist because you'd be getting 0 over 0. But that the limit as x approaches 1 of our function g of x did exist and was equal to 2. What about f of x? Well, first of all, let's ask the question, what is f of 1 going to be? Yeah, f of 1 is 2. Just peel that off of our table here. What would happen if we took a limit as x gets closer and closer to 1 of f of x? I mean, if we looked at values of x that are really close to 1, what are the outputs going to be really close to? Or?
2.
Yeah. Also 2. In this case, these 2 values ended up being the same. If you plug in values of x that are close to 1, you get outputs that are really close to 2. And also for f of x, if you plug in 1 exactly, you would also get 2. The values near x equals 1 are going to have outputs that are very close to the output you would get at 1 itself. Whereas if we contrast that with g of x here, if you plug in values of x that are near 1, we get outputs that are very close to 2, but at the point 1 itself, we don't get an output at all. And as for this one, this graph f of x, at the point A that I drew, we have an output of 2, but at values close to A, we have outputs that are close to 1 instead. So the idea of a limit of a function as x approaches A, for these 2 functions we looked at 1 specifically, where things were getting juicy. Here at A, this graph, at this A I drew, things are getting interesting. You could have a limit tell you something about a function at a point, not at the point itself necessarily, but at the points that are close by to it. What questions or comments do you all have for me thus far? Yes?
Do you do the f of a equals 2 graph again?
Sure, go over this one. So for this one, I said that f of a equals 2 because if we go to the x value of a, right here, if we look at what's the y value on our graph corresponding to a, it looked like we have a y value at this point. Since it's filled in here, we go to see, oh, f of a is going to be this y value, which corresponds to a y value of 2. But I think we said that the limit as x approaches a of the function turns out to be 1, because if we look at values of x that are just a little bit to the left or a little bit to the right of 1, of a, and yes, I know I said right as, I drew an arrow on the right side as I said left and vice versa. But if we look at values of x that are just a little bit off of a, we're going to get y values that are very, very close to 1. Like this y value is going to be very close to 1, this y value is going to be very close to 1, rather than 2. So even though f of a itself is 2, the limit ended up being a different value entirely, namely 1 in this case. Does that answer your question?
I'm still confused how limit is 1 and not something close to 2.
Good question. The reason is because the limit does not have to necessarily be anywhere different. I'm going to start that sentence over. The limit doesn't necessarily have to be anywhere near what the actual value of the function is. If your function jumps up and behaves very differently at the point, let's say a in this case, I'm sick of saying A. I'm going to say 3. So I have a specific number. Fine. In this case, if we look at value, in this case, f of 3 is very, very different than f of 2.9 or f of 3.1. Values of x that are getting really, really close to that x value of 3, but are not necessarily going to be 3 themselves. Now you might ask, Dr. Gerstle, what would a formula for a function look like that would cause something like this to happen? And usually it would be a piecewise function. So in order to get something like this, you would need, I don't know, f of x equals, I've written myself into a corner. X cubed. If x is anything other than 3, but if you plugged in 3 itself, you would get 2 as an output. That would be the sort of function that would produce a graph like this, a function that we explicitly say, I want this function to behave differently at 3 itself than at all other values of x, including values of x that are really, really close to 3. And what this is going to give us, as I think Ronan pointed out earlier, is an example of something that's going to be discontinuous at 3 once we get to our next standard. A function that behaves differently at that point 3 rather than all of the points close by. G of x was another example of that, where at 1, g of x behaves very, very differently than any other value of x. You plug in x equals 0.999999999. You're going to get g of that as 1.9, insert an appropriate number of 9s. No matter how close you get to 1, as long as you're not at 1 itself, g of x is just going to return 1 greater than that. But if we were to plug in exactly 1, and only exactly the number 1, g of x explodes. Think of g of x as being like a computer, and you tried to say, computer, tell me what 1 is as your output. G of x would say, does not compute. Give me better inputs, etc. We're going to look later on and see some like real-world examples too of what might be a scenario where that sort of thing occurs.
Is it possible to have a limit that doesn't exist?
Ooh, is it possible to have a limit that does not exist? Stay tuned. Spoiler alert, yes. But in order to have a limit that does not exist, you either need to have something where the limit from the left and the limit from the right are not equal to each other, which we'll look at an example of where that occurs once we define one-sided limits. Or you need to have something pathologically crazy, which we will also take a look at, but I don't want to spoil right now if that's okay with you. Good question. That's a good question, though. Is it possible to have a limit that does not exist? Because in all 3 of these examples, the limit did exist, even though the function itself happened to not exist for this one at the point itself. It's going to turn out it is possible to have a limit fail to exist, but we have to go a little bit more clever to find examples of what that might look like. These are all good questions. I'm glad you're all asking. Any other questions or comments? For now? Alrighty. In that case, let's evaluate some limits. And this time, we're going to see if we can evaluate them without having to necessarily rely on a graph. So let's start off with, I'm going to find a limit, I'm on page 3 now, as x gets close to 2 of x squared minus 5x plus 6 over x minus 2. So we have a function, we have some expression, and we want to say if we were to plug in values of x into this expression right here, that are really, really close to 2. Like if we're plugging in values of x that are like 1.9, 2.01, 2.0001, what sort of outputs would we expect to be getting? So first of all, what would happen if we tried to plug in 2 for x? If we just plugged in 2 itself into this expression.
Isn't that fine?
Why is that?
Because when you plug into the denominator, it would be over 0.
Golly. Yeah, so if this is our f, let's call this f of x, just to make it easier to talk about. If we tried to plug in f of 2, we would get a 0 in the denominator, which is sad. We'd also get a 0 in the numerator, funny enough. We would get 4 minus 10 is negative 6 plus 6 is 0 as well. So f of 2 does not exist. That doesn't necessarily, but as we've seen, that doesn't necessarily mean that the limit as x gets close to 2 does not exist. Because it's totally possible that if we plug in values of x that are really close to 2, they all get really close to being the same finite numbered output, as we saw with g of x in the first page. So, anybody have any ideas? And in fact, spoiler alert, that is going to happen in this case. Does anybody have any ideas? How would you find the y value that f of x would be getting really close to for values of x that are near 2?
Well, I think like the last function we did, if we factor out the x minus 2 from the top expression, it'll probably give us what the expression that would give us not a whole where there is a.
Oh man, that's quite the sentence right there. I'm gonna have to ask you to talk to your English professors about that one. But so you're suggesting that we factor the numerator and see if there's something nice that cancels out in the top and bottom? I like it. Yes?
I'm not quite sure about this, but because the highest power is 2 on the top and it does not the same on the bottom, you can tell that like because it's the bottom part is x minus 2, and you know that 2 would be more than limit. Like you could check that to see if it's the limit at 2. That makes sense. Sorry, there's a bit of a garbled sentence, but.
Man, it's hard to have good sentence structures when you're doing math sometimes. Heaven knows I've said my full share of rubbish at the front of the classroom. So what you're let me see if I understand what you're saying. So you're saying that that the highest power of x of the numerator is going to be x squared, and in the denominator it's an x.
Mm-hmm.
So you're suggesting we plug in 2 into both of those and do like 2 squared over 2?
No, I mean, how do I explain? Never mind.
Be happy to talk to you later if you like about it.
Okay.
You don't want to know. Yeah. I think what you suggested is going to be what we're eventually going to do when we take limits as x goes to infinity. We would end up doing something like that. Just say, only the highest power of x matters. But turns out we can't do that. Specifically that in this case here. I'd be happy to talk to you later though if you kind of have a way to better formulate your question.
Could you do x minus 2 and then x minus 3 on the top and then cancel out the x minus 2?
Ooh, okay. So sounds like you have an idea for. I'm sorry. How did you factor the numerator?
Well, -2 plus -3 is -5, and -2 times -3 is the 6. So I just factored the polynomial.
Okay. You factored x squared minus 5x plus 6 to get x minus 2 times x minus 3?
Yeah.
I like it. Because if we multiply this out, we would get, if we were to FOIL out this expression, we would be getting x squared from the first 2 terms. The outer 2 terms would give us a minus 3x. The inner terms would give us a minus 2x. So minus 3x minus 2x would give us a minus 5x. And then the last 2 terms, the outside terms, would give, or not the outside, the last 2 terms would give us a -2 times -3 is positive 6. Yeah, I think we could certainly factor x squared minus 5x plus 6 in this way to get x minus 2 times x minus 3 all over an x minus 2. And so then you propose we cancel out the x minus 2 factors in the top and bottom.
Yes.
Can we do that?
No, because we don't have 0 on the bottom.
Are we going to be we said earlier on that you have to be I tried to say you have to be careful about canceling, and it came out as you have to be you have to be careful about canceling the same term out from the top and bottom, because if that same term was 0, we couldn't cancel that out from the top and bottom. Do we have to worry about that here? So specifically, at x equals 2, we couldn't do that, because at x equals 2, we'd be getting a 0, this term would be 0, this term would be 0, we'd be canceling out a 0 from the top and bottom, and sad times would ensue, because that's illegal. Seriously, if you did that, I would have to call up security. And since they've stolen our entire parking lot, they'd be able to come quickly and they would arrest me. Do we care about what happens at x equals 2 itself in this expression? Why not?
Because we're evaluating limits are really, really close to 2, so if we know if we plug in actual 2, we're just doing a quick way of solving the closest, or the values around it.
Yeah. Since we're taking a limit as x gets close to 2 and doesn't equal 2, if we were to plug in, say, 1.99 for x here, we would be getting something, this term would be very close to 0, but it wouldn't be 0. And as long as it's not exactly 0, we can cancel it out from the top and the bottom. So in other words, for values of x that are only getting close to 2 rather than being equal to 2, I actually think we can cancel out factors of x minus 2 from the top and bottom. Because we're only going to be canceling out numbers that are close to 0 from the top and bottom. And that's okay, rather than canceling out 0 itself from the numerator and the denominator. I'm going to make a note of this here. You can cancel out factors of x minus 2 from the numerator and denominator. Because for x close to 2, but not equal to 2, x minus 2 does not equal to 0. And it's okay to cancel out the same term from the same factor from the top and bottom as long as you're not canceling out 0. Somebody in the back had a hand up earlier. Anybody have a question? So what does that leave us with? Well, if we cancel out our factors of x minus 2 from the top and bottom, we're going to end up with a limit as x goes to 2 of x minus 3. And here's the kicker. As x gets really, really close to 2, what can we say about what x minus 3 is going to get really, really close to?
-1.
How did you get that?
Because you can just plug in x equals 2 at this point. Like, you're not actually plugging it in, but like you're pretending to, kind of, and then that gives you the answer, -1.
Yeah, we can say that while this original starting expression was very poorly behaved at 2 itself, x minus 3 is pretty nice. Behaves nice at 2, behaves nice very close to 2. So at this point, we can actually just plug in 2 for x and get a final answer of -1. So in other words, when we take a limit as x only gets close to 2 of our function, at x equals 2, our expression's undefined, but for values of x that are really, really, really close to 2, we're going to get outputs that get really, really, really close to -1. Meaning if you were to plug in something like x equals 1.99, I'm going to guess that you would get an output that's something like negative 1.001. Inputs close to 2 give you outputs close to negative 1, even though 2 itself does not work as an input. Yes?
So, on the first page, our limit, which was limit of g of x was 2.
Yep.
Which is the average of x equals 0.
Here, I'm gonna write this. I want to write this one down again. That's the one that is x first one.
So you plug in x equals 0, you get an output of 1.
Mhm.
X equals 2, you get an output of 3.
Yep.
The average of those is 2.
Indeed.
So I solved it and I got negative 1. I just don't know if the logic holds. So I plugged in a whole number value less than 2, which is 1, a whole number value greater than 3, or greater than 2, which is 3, and then took the average to get negative 1. Does that hold?
Ah.
And negative,
so
negative
interesting.
1 was the limit. So
That's not always going to work, and I'll tell you the reason why it worked in both this example and the example from the front page. The reason why it worked in both of those examples is because you had a straight line.
Linear function.
Or a straight line other than at the point 1 on the front page, other than at the point 2 on this page itself. So if we were to try and graph this, it would look something like that, approximately. And if your graph is a straight line, then you can always find what the output, let's say this was filled in. You could always find the output at 2 by taking the average of the output at 1 and the output at 3. But if our function was something that behaved a little bit differently, like let's say this was our function, where this is f of 3, this is f of 1, we'll put a big hole here, and you wanted to take a limit as x gets closer to 2, the average of f of 1 and f of 3 would not give you f of 2. It happened to work out nicely in these first two examples because when you simplify down, you get things that just behave like straight lines, but that's not always necessarily going to be the case. Like in this case, for instance, when we cancel out the x minus 2's, we saw, well, this everywhere except at 2 itself, this is going to behave just like y equals x minus 3, which is a straight line. But you can't always guarantee, and in fact, in most cases, that's not. It did in the first two examples because I wanted to ease you into it a little bit. But does that make sense?
Yeah.
Good question. And by the way, that's the sort of question I think is a great one to ask as a mathematician. Like, oh, I'm noticing this pattern seems to be occurring. I wonder if this pattern occurs in full generality. And that question right there is the essence of what it really means to do math. I'm gonna put on my nerd hat for a second, in case I wasn't being nerdy enough already. Say, that's why I find math so cool. And that if you were to ask me, Dr. Ursel, how would you define math? I would say math is the art of finding patterns like that. Of like finding patterns and seeing, that's interesting. I wonder if we can show that this works in more cases, in all cases. Or if it works sometimes, but not always, which is going to be the case of this, the limit is just the average of plugging in the number 1 above and 1 below, which doesn't always happen. But asking and answering those sorts of questions is really what it means to do math at its core, or more generally, what it means to do science. That's the whole scientific method. You form a hypothesis, you try and answer it, you see if it holds. Doesn't necessarily speak to everyone, but I think answering those sorts of questions is really cool. Anybody else? I was going to give you all a few minutes to work on the rest of the page. I tell you what, I'm going to lay you out a couple minutes early, but give you all some homework then. See if you can figure out the rest of this page. And we will start class off on Wednesday with a quiz, and then after that we'll come back to this packet and keep going from there. So So in class on Wednesday, we're going to continue looking at limits, look at something called one-sided limits, and then Nora, we'll see if we can answer your question from earlier of when is it possible to have that the limit itself does not exist. The answer is, can you just plug in values really close and see? In practice, that often but not always works. We're going to have a big lesson about that in Wednesday's class. So stay tuned for Wednesday. In this case, that probably would have worked out, but you could also have very pathological examples where you're just trying to guess and check, sort of like that, won't actually work. All right, hold on. Before I answer more questions, I'm going to stop this.